So my talk is dedicated to our approach of automatization of calorimeter R&D cycle. The main principles of this approach can be generalized for any detector R&D. So in the first part of my talk, I will touch some general aspects of applicability of the approach to detector simulation. And in the second part, I will tell how we apply the approach to LHCb, Electromagnetic Calorimeter Upgrade project. Let me define the aim of our approach. It is finding a function that describes the physics performance at a given total cost of the detector. There are a few possible scenarios here. First of all, the physics performance can vary from the selected reference physics process up to entire physics program of the huge experiments like the LHC. The total cost is also can be defined in different ways. For instance, it can include the existing infrastructure in a case of the upgraded detector or not. It can cover the simulation expenses or not. So let's leave that for now. This timeline shows the increasing interest to the intersection of high energy physics and machine learning in case of calorimeters. So the papers dedicated to the application of machine learning to the reconstruction events in calorimetry are on the light green background at the top. Corresponding applications to the simulation for calorimetry are at the bottom. We highlighted our papers with the red font. And let me remind some basic knowledge about calorimeters in high energy physics. The figure on the left shows the parameterization of the longitudinal electromagnetic shower profile. Note that the showers induced by different particles like photons and electrons are markedly different by the constant. The figures on the right shows the electromagnetic shower development. The fraction of the lateral shower width is parameterized using Moliere radio, and the longitudinal shower depth is also can be parameterized. Capital Z is for the atomic number of the calorimeter material. The energy resolution is also can be parameterized using this formula. We are well aware about the simulation drawbacks. The detailed simulation can be very slow in case we want to cover all possible options of the future detector. Fast simulation can be a good alternative, but it still can be inaccurate when addressed the result of some complicated effects. For example, spatial resolution of large angled particles or of the sidebands of invariant mass distributions are poorly described by such calculations by the majority of fast simulation techniques. Otherwise, that fast simulation requires fine-tuning. And we provide alternative approach we'll see later. And on this slide, you can see conventional constituents of detector R&D in our approach. It's general, not only in our approach. So it is for the simulation, especially at high pile-up conditions. But the pure signal events and some average pile-up contribution can be modeled and selected or using some signal and background populated regions of the detector. In case of reconstruction, overlapped signal and background events use background subtraction, and which is a calorimeter specific that clusters of calorimetric clusters can be reconstructed using its nested association with tracks and with tracks with vertices, and also using time information. And despite the fact the complicated reconstruction following such a simulation can achieve an outstanding performance, the fine-tuning of many parameters comes with significant overhead. And on this slide, you can see the idea of optimal detector design in our approach. That we require to cover entire R&D cycle whenever it's possible. Then to define a proper physics metric representing desired properties of the detector. And then to realize each step of the R&D cycle from the first principles, or use some computationally cheap yet reliable alternatives. Then to build a pipeline on top of these steps, and finally evaluate the importance of each step of R&D cycle. One important note that we are not required to achieve the best possible performance at each step. Instead of this, our aim is a high degree of automation of the R&D cycle. In this sense, the approach belongs to the AutoML category. The majority of different kinds of detectors consist of sensitive elements assembled to models. The number of sensitive elements or number of channels contributes significantly to the detector complexity and its cost. Even when the number of channels is fixed, we can rearrange the models in many ways. This slide shows how we can solve the problem of arrangement of the models of the detector, keeping total amount of the models. For that, we need accurately simulated responses of given models technologies. We need the estimate of the cost of that technology in case we have options. For example, different granularities realized in the same models as the building blocks of the detector. We also need the metrics obtained from reference physics processes within required physics of, for example, pile-up conditions. And our aim is to optimize physics performance metric, keeping overall detector cost. In many cases, the full accurate simulation of such detector can be really expensive, and we need to find another way. On this slide, you can see the layout of a pipeline in which it is possible to realize the ideas I just said. It comprises 3 stages. The first is this particle generation and propagation. Common experiment event generation particle propagation software can be used here. And the second stage consists of accurate detector responses simulation, as well as the reconstruction. And third is for the metric calculation. And the optimization cycle itself does not depend on the models technology and this arrangement, on the reconstruction, the metric definitions, and so on. The main limitations for the differentiability of the metric as a function of tunable inputs for example, for current realization of the electromagnetic calorimeter in this pipeline came from, for example, in the detector response, in a Gent4 simulation of that responses. On the XGBoost model we use here, but neural networks can be differentiable, of course, and also that a piecewise constant function of model's position is also doesn't differentiable. And let's consider how to apply this approach to LHCb electromagnetic calorimeter. And there is also details about the computation expenses in our realization at the bottom. This is a electromagnetic calorimeter of LHCb experiment. This calorimeter is responsible for measuring energy and position of the particles. It consists of 3,500 models, and the size is approximately 8 by 6 meters, and it is placed about 12 meters from the interaction point, and comprised of these models of 3 types. The figure on the left shows the current calorimeter model arrangement. We call it this configuration of the electromagnetic calorimeter of the LHCb experiment. The physics performance of this configuration at LHC run 1 and 2 is our baseline. And this is a proposed future LHCb electromagnetic calorimeter configuration. This configuration is driven by the radiation dose maps. And the questions for this future calorimeter: what is the best configuration for given models within a fixed cost in terms of given physics metric? And what is the best way to arrange a certain number of new models? And this slide dedicates how we simulate the responses. We use Junt for responses, and this physics process is our reference process, is a signal process, and we also use LHCb Monte Carlo minimum bias samples for the background sample. On this 4 images on the bottom left, you can see how we can represent the events in the calorimeter clusters without, from the very left, without pile-up conditions up to the pile-up conditions for LHCb after its upgrade. And on the right side, you can see downsampling of these events to the actual granularity realized in the calorimeter. This slide I want to skip because Artem just said about the generative models applied to the calorimetric clusters, and this also, yes. So in our approach to how we realized this pipeline to construct the upgraded detector, we use also machine learning based reconstruction. And I'll repeat that we are not claiming that machine learning based reconstruction is better than best traditional approach for the reconstruction. Moreover, we are not pursue best performance of the machine learning reconstruction, but we put the attention to the simplicity and the robustness of the model we used. In this approach, we are looking for the cell contained maximum energy deposit, or we call it seed cell. Once the seed cell is found, we record energy deposits in 2 layers of cells of the same granularity around the seed cell. These are basic features for the regressor. To reconstruct both the energy and position of the particle, we use XGBoost or extreme gradient boosting on trees. Besides the energy deposits in mentioned 25 cells, we consider barycenter, reference time information, and various combination of these features. And our chosen performance metric is the width of the invariant mass of pi0 and also the width of the B meson. To reconstruct spatial and energy resolution, as I said, we used machine learning, and on this slide we compared the simplified parametric reconstruction with our implementation of XGBoost here, and these 4 images for the spatial reconstruction, and these images on the right are for the energy reconstruction. On the top, without pile-up, but at increased pile-up, machine learning reconstruction still shows meaningful estimation, while the parametric reconstruction not. And for the high pile-up conditions, Kahneman reconstruction should be fine-tuned in that sense. The benefit of usage of independent regressors for energy and position that by combining the ideal energy and the reconstructed position, vice versa, we achieve final metric decomposition and inner validation of each of the reconstruction steps. We also use time reconstruction using machine learning. In that way, on this two-dimensional histogram on the right, you can see how we discriminate two signals, where on the vertical axis is the difference of the time between two signals, and on the x-axis it is ratios over these two signals. And we can see the regions we can distinguish between these two signals. When we account all the possible options, that at the moment we have the thousands of possible configurations how we can arrange the models, different model technologies, and also I didn't mention the longitudinal segmentation option, and also the time information, and how can we rule them all? And the answer is the black box optimization problem. Consider this problem as this black box. And due to CPU cost of the setup, we want to reduce as far as possible the number of calls of the function to be optimized. Considering the R&D cycle as a black box optimization problem may be a proper solution here. The two main ingredients here are surrogate model, which approximates the true function, is cheap to evaluate, and in general, any regression can be chosen here. And also the acquisition function, which estimates profit for optimization and uses this surrogate model. One of the ideas how to implement surrogate modeling is to source each point in the fitted space from Gaussian distribution. This allows us to produce prediction for the next point. The figure on the right shows how the Gaussian process approximates function f(x) or sin x, or with only 14 observations sampled randomly. And this also predictions using this surrogate modeling include variance. This is using this Gaussian process, but it's also computationally expensive. And when we apply this approach to our pipeline, the possible answer is how to account all the options of the R&D cycle to use Bayesian optimization with Gaussian processes. And in that sense, the full optimization cycle will look as follows. We construct surrogate model over known history, find a maximum of expected improvement algorithm, evaluate suggested point using real physical simulation, and add point to the history, and repeat these steps. For example, in this plot, we have somehow ordered set of 21 configurations with a number of models as in the present LHCb calorimeter. So let's vary the inner to middle border of the different granularities, and just after 15 calls of this costly function allow us to achieve this optimal. Black box optimization is also can be done with local generative surrogates. If one can approximate evolution of a system by some differentiable surrogate, it might profit from methods of this type. In this sense, we can approximate a stochastic black box with a local generative surrogate. This allows to compute gradients of the objective function with respect to parameters of the black box. And this is my concluding slide. So the R&D process requires time-consuming computation steps to evaluate physics performance for different detector techniques and configurations. And some surrogate machine learning models may be used for most steps that necessary for evaluating quality of different solutions. Such models can be automatically trained on available data sets and provide possibility to consistently estimate the resulting physics performance. And using automatic trainings speed up the turnover of the performance studies and ensures consistency and uniformity of obtained results. Thank you for the attention.
Thank you very much. Are there questions? I believe nobody but organizers are left, but still maybe there are questions. And I actually have a question. Why do you need a machine learning for that after all? I can't understand that, because all you do is optimization, and it could be done directly. Why do you need machine learning to do that?
Because machine learning provides optimization of assembling 1,000 possible options. In other sense, we need a fine-tuning of how each technology combines to another technologies.
Okay, that's a valid point. Still, there are some problems with that. For example, when you use machine learning, you need to rely on your simulation data a lot, because if of course, you have some tools to verify your model, but do you check the stability of the result depending on the simulation models?
Yes, of course.
Okay.
We use our own tools for that. Yes, our pipeline is based mainly on a.
Yes, and you jitter the parameters of your simulation, like for example, physical models or what?
Yeah, we compare with so when we simulate conditions of the present calorimeter data taken periods, we can compare with it. So we can compare with the real data, and
yeah, okay,
it's some points of our observation.
Yeah, the problem is that a lot of application of machine learning and those things, they hit the wall when they understand that the simulation result is not ideal. Okay, thank you very much.
Thank you.